In the simplest terms, a black body refers to an object that absorbs and emits all frequencies of radiation. An actual black body is an idealized object, and as far as we know, there is no actual object that can achieve this. We can, however, use the theory of a black body to help explain all of the real bodies around us. We know that all objects emit electromagnetic radiation. You may or may not remember way back in Physics 1 where we talked about the intensity of the radiation having to do with the absolute temperature of the object. The radiative power of an object is dependent on the temperature in Kelvin to the fourth power. For example, if we double the temperature of the object, the intensity of the radiation increases 2 to the fourth power, or 16 times. Now, all objects emit and absorb radiation in varying amounts. A black body is a theoretical object that will absorb all radiation that comes into it. We can apply the second law of thermodynamics here and say that a body emits radiation exactly as well as it absorbs it. Otherwise, any object in your room would be absorbing the energy around it, making it heat up and the room colder. And we know that this doesn't happen. So since a black body can absorb all radiation, then it will also be able to emit all radiation if we heat it up. This radiation emitted from a hot black body object is given the term black body radiation, and this ideal radiator would have an emissivity of 1. We cannot measure from a true black body object, but we can come pretty close. A small hole punched into the side of a large box works well as a near-perfect absorber. Any radiation that enters the hole will bounce around inside the box, and the chance of it ever getting back out of the hole is close enough to 0 that we can say that it will never get out. In order to get a near-perfect emitter, we do the reverse. If we have an oven with a tiny hole in the side, then the tiny amount of radiation coming out of the hole will have the same temperature dependence as the radiation intensity inside. So for whatever temperature we have inside the oven, the radiation coming out of the hole will nearly perfectly resemble the radiation that would be emitted from a black body object at that temperature. We can pass that beam of radiation through a diffraction grating and measure the intensity of the different wavelengths of radiation. Of course, then, we can graph the intensity of each wavelength. The graph then looks at the spectrum of radiation that is emitted by our black body radiation. The intensity of radiation is plotted on the y-axis, while the wavelength in the measured radiation is plotted on the x-axis. This graph of black body radiation has measured 3 different radiator temperatures. Notice the line for 3000 Kelvin and the line for 6000 Kelvin. When the temperature doubles, the radiation intensity increases by a factor of 16, just like the Boltzmann equation predicted. Also notice that as the temperature increases, the wavelength of the peak intensity shifts to the bluer end of the visible light spectrum. So as we increase the temperature of our object, we will also increase the frequency of the radiation that is given off. Notice that at a temperature of 3000 Kelvin, the object will emit radiation at a frequency that corresponds to the color red. Radiation emitted from an object at 6000 Kelvin will peak at the frequency corresponding to the color green. Experimentally, we have found that the peak wavelength is directly proportional to the absolute temperature. This is known as Wien's law. This equation is essential in areas of study such as astronomy, where it allows us to determine the temperature of stars simply by looking at the radiation they give off.